This is a review. Since it's probably going a little bit fast last time. So we imagine there was an information source. And it's a IID, independent and identically distributed information source, modeled by a probability distribution, X of X, and it emits a sequence. That's n, which we said we abbreviate X superscript n means there's n symbols, X1 through Xn. Then we talked about what is the scheme for quantum data compression. We mentioned the notion of typical set. Okay. So the typical set. It's the set of all sequences such that the sample entropy, I'll write it like this with a bar on top, meant to remind you of like sample mean. The sample entropy minus the true entropy less than some delta. You just think of delta as a small number, a small positive real, strictly thought. So the true entropy is this famous formula of Shannon, von Neumann, etc. And it's a measure of uncertainty. If you think of this function, negative log px as a surprisal, right? So we said, why is it surprisal? Well, for events that are unlikely, you would be surprised if they occur. So if they're unlikely, the probability is small, and the surprisal will be high. It's where if they're more likely, the probability is closer to 1, and the surprisal is less. Okay? You can then think of this as the entropy is the expected surprise. This is surprisal, measure of surprise. And you can think of this as the expected surprise. And then often it's just called a measure of uncertainty. Okay? One of many possible measures of uncertainty. But, and that raises an interesting point. So why is this function interesting? Well, that was the point we were getting to at the end of the last lecture, right? It's interesting because it has an operational meaning, as a physical meaning is the data compression limit of an information source, right? That's the main statement of Shannon's data compression theorem. I'll just abbreviate this SDC, Shannon data compression theorem. It's entropy is equal to the data compression limit. So it's a very important result. You know, you can call it fundamental theorem 1 of information theory. And then we're going to try to get to fundamental theorem 2 of information theory today, which is something else that I'll get to. Okay, so then we argued that from the law of large numbers, the probability that a random sequence, so when I write capital N, when I write capital X to the N, I mean a random sequence, a random variable with individual, it's made up of random variables X1 through Xn. So the probability that a random sequence lands in the typical set is larger than 1 minus epsilon. And the statement is so this is true for all epsilon between 0 and 1, delta greater than 0, and sufficiently large n. This is the like blah 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 epsilon delta from real analysis or like definitions of limits that you learn about in math. Right? So it's that kind of statement, and you just read it as saying it's highly likely that a random sequence will land in the typical set if n is large, sufficiently large. Okay, that's how you read it. And this kind of thing we'll see a lot. We'll encounter when we start coming to more of information to this. One thing I didn't talk about was the size of the typical set. Okay, so we did mention it, but we didn't prove it. I want to show you that real quick because it's very simple. So the size of the typical set is no larger than an exponential in the entropy. Okay? And then how does this compare to the size of the set of all sequences? What is the size of the set of all sequences times the alphabet size to the n? Right? That's the size of the set of all possible sequences. And then we can rewrite this as 2 to the log pi, 2 to the n log pi. Okay? And this is indeed true. I mean, it's obvious that this is the size of the set of all sequences. What's less obvious is that the entropy is less than log pi. But, you know, this is a statement that the entropy is always less than the logarithm of the alphabet size. Okay. When is this inequality saturated? Inequality is saturated when the random variable is the uniform probability distribution. Okay. So if I plug into this entropy formula 1 over d for p of x, I'll get log d. I can factor that out. It's sum over 1 over d, which is just 1. Right? And then it'll evaluate to log d. So this inequality is saturated by a uniform random variable. The other thing we know about entropy is that it's non-negative. Okay, it's always, it can never go negative. So this is true as well. That's a pretty simple proof, right? Like negative log of a number between 0 and 1 is non-negative. If I take these non-negative numbers and multiply them, I get a non-negative number. So that's, you know, pretty simple. What is the lower bound saturated? It's saturated for a completely deterministic random variable. That might sound like an oxymoron. You know, they're what's called random variables with degenerate probability distribution, where the probability distribution is just a delta function. You know, it's just like a spike of 1 for one value and 0 for the other. So it's a deterministic event. And in that case, the entropy, you know, it makes sense that the uncertainty would be 0. Deterministic random variable. Right? These are the two. This one's saturated by a uniform random variable. This one's saturated by the degenerate, let's say deterministic random variable. Okay, so those are the different extremes. And then what is this? What can you deduce from this? Well, if there's any gap, the random variable is non-uniform, then there will be a strict inequality here. That is true. I don't know if that's really true, but it is true. And then what does that mean for the gap between the size of the typical set and the size of the set of all sequences? It means there's an exponential gap, right? This one will be exponentially larger than this one. So that's the kind of savings you get in data. Right? Any questions about that? All right. So let's prove this statement. I think it's an interesting proof. It's four-liner. Number one is equal to all of the probability mass. Okay, and when I write this notation, we defined it before, but this Pxn, xn, means the n-fold probability distribution. So take all the symbols in the sequence and you plug them into this distribution, you multiply. Because we're making the assumption of independent. Independent means multiply identically. Px is the same for all. Okay. So we're trying to prove this statement down to the size of the typical set. We start with this basic fact, and then we can truncate the sum to be only over the typical set. Okay? The typical set is smaller than the set of all sequences. Then you can use this definition. I apologize, I didn't define sample entropy. Negative log X and sample entropy. Okay. So you take this definition of typical set, and this bounds, an absolute deviation of the sample entropy and the true entropy. You rewrite it, and then you can get a lower bound on this probability when you're in the typical set. Okay, so that lower bound will be a uniform lower bound. Two to the minus entropy x plus the little delta. Okay. Now what? Well, we have a uniform quantity here that's independent of the sequences that we're summing over. So this sum is just now, we can rewrite this as the size of the typical set times 2 to the minus n h of x. Okay. Then you did the whole thing, you bring this to the other side, you get that. All right? That's the proof, and just amounted to looking at the probability of the typical set, which, by this statement, the probability mass in the typical set is pretty much equal to 1. Right? It's pretty much all the probabilities mass is there. However, number of sequences is much smaller. Okay? So this is a special case of a more general phenomenon called measure concentration. Okay, so and this is related to what the law of large numbers says. As n gets larger, the probability mass tends to concentrate on this much smaller set. It's like all the probabilities accumulated there. You're not going to find. It's going to be very unlikely that you'll find a sequence outside the typical set. Okay. And this is similar to what happens when you pick a point uniformly at random on a hypersphere. It tends to concentrate around the equator. Right? It's like totally weird according to our intuition of the everyday world. But that's what happens mathematically. Like even if you pick points uniformly around the sphere, it's highly likely to end up on the equator. Okay. It's similar to like the central limit theorem. There was someone here last time asking about central limit theorem. In these large n limits, you tend to concentrate on the small bands, right? Like if this is the true mean, this is mu plus delta, mu minus delta. Then law of large numbers, central limit theorem, some statement saying that when you pick a large number of random variables, you'll end up with this small band centered around the beam. And it's highly unlikely to find it. That's precisely what's happening. Right? Just another instance of that kind of thing. It was much more novel in the time of Shannon. Okay. All right. So then the scheme for data compression was just keep the typical sequence. Okay. And then if we did so, we found that the data compression rate to bits per symbol, right? Number of bits per symbol. For us, what we said was we would keep only the typical sequences. We would, for each one that we had, we would do a binary encoding, a binary set of size no larger than this. The number of bits that we need to encode this set is binary logarithm of this number. Right? So the binary logarithm of that is n hx plus delta. Per symbol, how many symbols are there? Well, there's n. It's a length n sequence. So divided by n, you get entropy plus the delta. And now you say, like, okay, well, we proved that this limit is achievable for all delta strictly greater than 0. Then once you've done that, you're allowed to think the limit is delta goes. You're not allowed to take it at the beginning, you're allowed to take it. So then, what does all this say? The entropy is an achievable rate for data compression. I think I don't want to go into any more than that, because like with the 50-minute lecture, we're now at the halfway point. There's all kinds of things we want to do. Any questions? Yes.
I'm still a little caught up on how you get from the line. Yeah, so I guess it would be that one to that one.
Right. Take this definition. On the camera, so I'm not. So that's this statement rewritten, right? Right now, move h of x to both sides. Right? Now multiply by n. Right? And now do 2 to the minus. Right? And then one of them will end up being this. Okay? Yeah. Okay. Other conceptual questions? All right. Good. One thing I didn't say, we only proved one side of this theorem. We proved that the entropy is achievable. What we didn't prove is that it's impossible to have a lower compression rate. Okay, that's so one thing. The thing that we did is we proved what's usually called the coding theorem, because we exhibited a compression scheme or a coding scheme. What we did not prove is what's traditionally called the converse statement. Okay, So the converse would be that if you try to compress the rate lower than the entropy, then you'll not be able to make the error go to zero. Okay. That is true. We won't do that now. Okay. But it's very important because it tells you, all right, I have a way to achieve that limit, and you're down here. And then if I try to go lower that limit, you can't do it. There's even something called strong converse, where if you try to go lower than the data compression limit, actually the error probability will tend to 1. It's the worst possible thing you can do, go lower than the data compression limit. Okay. All right. Okay, let's talk about channel coding, error correction, communication over a noisy channel. Okay, and the way we're going to model the communication channel classically a conditional probability distribution. So you put into the channel a symbol X, and randomly out comes a symbol Y, which may be different from X. There's like these stochastic transitions in the channel. And that's meant to model what we encounter in reality, right? Like we don't have perfect communication channels. The classical computer might seem like a perfect device, and that's quite a marvel that it works. But there are even imperfections that the hardware makes it good. You probably never notice, unless you have Windows. So okay, so that's how we model a communication channel. And the simplest possible example of a channel, which is worthwhile to study, is called the binary symmetric channel. Okay, it looks like this. You put in 0 with probability 1 minus p, you get 0. With probability p, you get 1. You put in 1 with probability p, you get 0. With probability 1 minus p, you get 1. Symmetry is that 0 gets through faithfully with probability 1 minus p, as well as 1. And then a bit flip from 0 to 1 or 1 to 0 occurs also with the same probability p. That's why it's called symmetric. It's just the symmetry. Okay, so what is the simplest possible idea for error correction? Okay, and to make the channel interesting, the probability is strictly greater than 0 and strictly less than 1. Otherwise, it's a deterministic channel, and well, there's nothing worth studying there because it's perfect. Okay. So the simplest possible idea for error correction is what we're doing all the time over Zoom. Like someone doesn't talk loud enough, and you say, "Can you please repeat what you're saying?" Right? Shout it louder, which is like amplifying the signal, effectively copying, right? So the simplest scheme for error correction is called the repetition code. Okay. And let's analyze this repetition code. You encode 0 as 000, so you repeat it 3 times. Right? You encode 1 as 111. All right. What is the rate of this? What is the rate or the efficiency of this code? 1 information bit per 3 physical bits that you send over the channel. Okay. So the rate is bits per channel use. And in this case, we can send 1 bit for 3-channel use. We would use the binary symmetric channel 3 times, right? So you send 0, you send it through, it gets through with probability 1 minus p, otherwise it flips with probability p. And then we assume it's IID, so the next time we use it, same thing. It either gets through with probability 1 minus p or gets flipped. The same for the variable. Okay, so we'll assume IID again. Right? So how can we describe channel out in terms of probabilities? What we want to understand is when error correction gives an improvement. Right? So the way you should think about this is that there's nothing you can do to change the physical channel to come up with some kind of like systems engineering solution, which is this code. Right? So when does error correction help? So that's the question we want to answer. And we'll try to figure out for what values of p error correction will help. Okay. Let's do the analysis. Some channel output is described by this. Make a table with output and probability. So 0, 0, 0, the probability that, and we'll assume the input so we'll assume that we're sending in, we want to send the 0 bit, which we encode as 0, 0, 0. What is the channel output? Okay, and then we'd actually have a very similar table for when we send 1 through, we'd have to flip all the 1s and 0s. Okay, so what is the probability when we send through 0, 0, 0, we get out 0, 0, 0? Well, if it's IID, it's going to be 1 minus p multiplied 3 times. Okay, so 1 minus p to the 3rd power. What is the probability of a single bit flip? So those are other possibilities. So the probability that if we put in 0, 0, 0, we get out 0, 0, 1. That'll be 1 minus p squared for the 2 zeros, and then p for the one that flips. And then because the channel is IID, there's the symmetry, and the probability will be the same for each of these. Okay. Okay. Then probability of 2-bit flips. Similar reasoning. Now it's p squared 1 minus p. And then the worst possible scenario is that all the bits flip, and the code word completely flips to the other code word. Right? So that's a problem. Okay. How should we decode this? We can use a very simple idea, majority vote decoder. Okay. So the majority vote decoder, it does exactly that. You look at the bits, and if more of them are 0 than 1, you decide 0. If more of them are 1 than 0, you decide 1. Okay. So under this decoder, 0, 0, 0, these all get decoded to 0, 0, 0, and these other abilities get decoded to 1, 1, 1. Or we get decoded just 0, 1. Like it's decoded as the message that was transmitted. Like, if you want to draw a picture for this, here's a nice picture. These are the kind of pictures we're drawing. This is meant to fit the full code. Right? This is a single bit, gets encoded as 0, 0, 0, 1, 1, 1. Actually, nice. I is 0 or 1. Okay. And then at the end you make some estimate of I. Right? Let's kind of diagram to describe this problem. N is the noisy channel. So N is this. Okay. So what is the probability of an error when transmitted at 0? What's the total probability of an error? It's going to be the sum of each of the probabilities of these ones, right? Because like if you send 0 and you decode as 0, well, is it a corrector? If you decode as 1, that's an error. Right? So what is the probability? It's going to be the sum of these individual ones. So p cubed plus 3p squared minus, times 1 minus 2. So 3 because of these 3 individual codons. Okay? That's the total probability. And then if you add up, so this is the probability of error when you set through 0. Okay. And then if you were to add this probability of error when you send 0 to this entry and 3 times this entry, it would sum up to 1. So probably would be 1. Okay. There's a similar result when sending 1 through the channel due to the symmetry. Okay. So, the probability of error when sending 1 is going to be the same number. That's due to the symmetry of the channels. Right? We plug 0 and 1 everywhere, and the channel is the same. Okay, so what is the total error probability? So we'll call that, I'll abbreviate ERR to E. And be the probability of error when you send 0 times the probability you select 0 plus the probability for the 1 case, when you send for 1. Okay? And these two conditional probabilities are the same. Right? And then we know that the probability of 0 and the probability of 1 sums up to 1. So then this is just going to be, you do a calculation and you get 3p squared minus 2p. Okay. So to address this question at the beginning, when does error correction help? Well, suppose you do no coding at all. Right? What is your error probability? P. Okay. So when does error correction help? Well, it's when this error probability is less than 2. That's the answer. When 3p squared minus 2p cubed is strictly less than 2. All right. You work this out, and you get that this is equivalent to 0 being less than p times 1 minus 2p times 1 minus p. This is satisfied for p strictly less than 1/2. Okay. We already knew that p was a number between 0 and 1, non-negative. Actually, we assumed that p was strictly between 0 and 1, so then this is strictly greater than 0, strictly greater than 0, and then you're left with looking at this one. So when p is strictly less than 1/2. what happens when P equals a half? That's the worst situation. With equal probability, the output is 0 or 1. And then if you, so when P equals a half, that's the worst possible scenario. If you were to pick a prior distribution of the input, and call that some random variable x, right? And then use this distribution with P equal to a half, and model the output as a random variable y, x will be independent of y. Okay? So what you get at the output has nothing to do with the input in that case. The channel is completely useless. It's like the wire has been cut. Okay? Nothing can, it's like you're not even looking at what's coming, you're just like looking at the time. So, however, if P is strictly less than a half, you do this code, and you can reduce the error probability from order P to order P squared. Okay. That's an improvement. We have 6 minutes. So it's an improvement. Error probability goes from order P to order P squared. Okay. However, at the cost of 3 physical bits for 1 information bit. Okay. We can do what's called concatenation. Okay. So we can do the encoding not once, but twice. And what do I mean by this? So we'll now flip things a bit and call this a concatenated repetition code. So I do the code once, and then for each of these physical bits, I then do another encoding. So this would go to 0, 0, 0. This would go to 0, 0, 0. 0, 0, 0. That's the next encoding. And 1 on 1, 1 on 1. You might ask, well, why didn't you just do 4 or 5? If we do it this way, I can recursively apply this analysis. Okay. So that's the only statement that I want to make, is that now when you do this concatenated repetition code, 1/3 goes to 1/3 squared. Okay. And then you'll go through this whole analysis. We found that on a first iteration, P went to 3P squared minus 2P cubed. Now I would take this, call this P prime, right? I would plug back into this formula, get the new error probability. So it'd be 3P prime squared minus 2P prime cubed. Leading order, P to the 4th, right? And this first iteration went from P to P squared. Now we're going to go from P squared to P to the 4th. Okay? So that might be a little fast to see that, but when you run through it, that's what. So the error goes is I'm going to write this P squared squared. Right? And so we made, okay, with this further repetition, it's kind of intuitive. You repeat more and more and more, the error is going to go down. That's the basic state you want to take. So what we're doing just allows us to analyze that. So if we repeat, 9 times, we can make the error go to p squared, right? If we concatenate n times, the rate will be 1 over 3 to the n, and the error will be p to the 2n. Okay, so the basic point that I want to make is that we can rigorously show if we keep increasing the rate of repetition, then we can make the error probability go down as far as we want. Yeah. Yeah.
Right? So, I mean, how do you, is it per system, like per application, or is there kind of one model that represents the optimized number of repetitions for any
Oh.
system?
So this is a terrible scope coding scheme. This is just meant to illustrate that we can make the error probability go arbitrarily close to 0 as we want. However, the question you're asking about observation is extremely important. This is a terrible scheme. Why? The rate is going to 0 as well, right? So bits per channel use is tending to 0. It's terrible. Before Shannon, I believe it's correct that most of the world thought this was basically the only thing you could do. Maybe it's not fair to everyone else in the world to say that. I've read this in places. Is where Shannon showed that there are ways for channels, arbitrary channels, to have optimized codes such that you can simultaneously make the error go to 0 at a non-zero rate of communication. Okay, and then you can define something called the capacity of the channel, which is the optimal rate. And I believe we're out of time. So next time we'll get into Shannon's channel capacity theorem, and we'll argue that in principle there exist codes that can achieve what's called the capacity of the channel, the highest possible rate of communication, such that the error can go to 0 as the number of channel uses gets larger. Okay, so that was Shannon's core insight number 2, fundamental theorem 2 of information theory. First one, data compression limit. Second, channel capacity theorem. Okay, and yeah, it took a long time for people to figure out actual codes to achieve the capacity. Shannon gave a mathematical argument that in principle there exists codes. It was a very clever argument that allowed him to argue that there exist codes without having to explicitly design them. So what he did was he picked them randomly. That's a stupid idea, but it works well. If you have a large number of challenges. Again, due to measure concentration log numbers. Okay. Any questions?
Even with the concatenations, the P threshold P always means.
That's right. Yeah.
You can never do any better.
Yeah.
It doesn't make sense.
The people's a habit. I mean, you won't get the strict inequality. You won't get an improvement.
So what
Is it obvious with this one?
yeah, can we do any better than
The channel is given to us. In this class, we're assuming the channel is given, and we cannot do anything clever to, change the cable. Like we're just assuming the cable is given. We've done some characterization of it to learn this like channel law, and then that's what we have to deal with. And then we try to design error correction codes to achieve perfect communication, like asymptotically perfect communication as a non-zero rate. Yeah. So I mean, like, what we'll find is if we encounter this similar situation, the P1/2 situation, but where the output random variable y for the general case is independent of x, the channel capacity will be 0, and there's nothing you can do about it. However, if that's not the case, the channel capacity will be strictly non-zero. All right. See you Friday. Oh, yeah. This is a law.